The shell model of the atom is a fundamental concept in chemistry and physics, providing a framework for understanding the complex structure of atoms. At its core, the model describes how electrons are arranged around the nucleus, orbiting in layers that resemble shells. This arrangement is not arbitrary but is dictated by principles that ensure the stability and chemical properties of the atom. The significance of the shell model goes beyond mere academic interest. It serves as the foundation for understanding chemical bonding, the structure of the periodic table, and the behavior of materials under various conditions. By comprehending how electrons populate specific shells, scientists can predict an element's reactivity and its interactions with other elements. To truly appreciate the model's value, one must consider its development over time. Initially proposed in the early 20th century, it has undergone numerous refinements thanks to contributions from many scientists. These enhancements have made the shell model a robust tool for predicting atomic behavior, crucial for advances in both theoretical and applied sciences. Electrons, those tiny particles buzzing around the nucleus, follow paths that are not as random as one might think. Their paths, or orbitals, are defined by a set of rules derived from quantum mechanics. These rules do not just dictate the path, but also the energy levels of the electrons, which in turn influence the atom's chemical properties. The arrangement of electrons across different shells can be understood through principles like the Pauli exclusion principle and Hund's rule. The Pauli exclusion principle states that no two electrons can have identical quantum numbers within an atom, ensuring that electrons fill up orbitals in a structured manner. Hund's rule further explains that electrons will fill an unoccupied orbital before they pair up in an occupied one, minimizing electron repulsion within an atom. This structured filling of orbitals creates the characteristic electron configurations that define each element's properties. For instance, the noble gases have complete outer shells, which make them extraordinarily stable and unreactive. Understanding these configurations allows chemists to manipulate and utilize elements in various chemical reactions, a fundamental aspect of chemical synthesis and materials science. Ionization energy is a critical concept in atomic theory, representing the energy required to remove an electron from an atom. This measurement is not just a simple number. It reflects the underlying electronic structure of the atom and influences how an element reacts chemically. Higher ionization energies indicate more tightly bound electrons, which typically translates to less reactivity. The first ionization energy is particularly telling as it provides insights into the valence electron's binding strength, the electrons involved in forming chemical bonds. As one moves across the periodic table, ionization energy tends to increase, a pattern that is crucial for understanding elemental reactivity and trends within groups and periods. Analyzing these trends, scientists can deduce the arrangement of electrons in an atom and predict its chemical behavior in different environments. For example, elements with low ionization energies are more likely to lose electrons and form positive ions, a property exploited in everything from metallurgy to biochemistry. The variations in ionization energy across different elements can be bewildering at first glance. However, these variations follow a logical pattern when examined through the lens of atomic structure and electron configuration. Elements with a higher nuclear charge, more protons in the nucleus, generally have higher ionization energies because the increased positive charge more strongly attracts electrons. Additionally, the distribution of electrons across different orbital shells significantly affects ionization energy. Electrons in outer shells are less tightly bound than those in inner shells due to increased distance from the nucleus and shielding effects from inner shell electrons. This explains why ionization energy generally increases across a period, as electrons add to the same shell but the nuclear charge increases. Understanding these factors allows for the prediction of ionization energies based on an element's position in the periodic table. This predictive power is crucial for chemists who use these properties to design new materials, and for educators who explain the intricacies of chemical reactions to students. Section 5. Helium versus hydrogen, a battle of the elements. Helium and hydrogen, the first two elements on the periodic table, serve as excellent examples to illustrate the concept of ionization energy. Despite having only one more proton, helium's ionization energy is significantly higher than hydrogen's. This difference lies in the effective nuclear charge and electron configuration of the two elements. Helium has two electrons filling its first and only electron shell, creating a stable, fully occupied shell. This configuration significantly increases the energy required to remove one of these electrons compared to hydrogen, which has only one electron in its shell. The additional proton in helium's nucleus also contributes to a stronger attraction to the electrons, further increasing the ionization energy. Moreover, the lack of electron-electron repulsion in helium adds to the stability of its electrons. In contrast, hydrogen, with its single electron, faces no such repulsion, making its electron easier to remove. This stark contrast in ionization energies between helium and hydrogen is a fundamental demonstration of how nuclear charge and electron configuration dictate an atom's chemical properties. Section 6. The power of Coulomb's law in explaining ionization energy. Coulomb's law, which quantifies the force between two charged particles, is instrumental in explaining the trends in ionization energy seen across the periodic table. According to this law, the force of attraction between the positively charged nucleus and negatively charged electrons is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. This relationship helps explain why atoms with more protons or a higher nuclear charge generally have higher ionization energies. The increased positive charge in the nucleus results in a stronger attractive force on the electrons, making them more difficult to remove. Similarly, as electrons are added to shells further from the nucleus, the increased distance reduces the force of attraction, generally lowering the ionization energy. Understanding Coulomb's law allows scientists to not only predict ionization energies, but also to manipulate atoms and molecules for specific purposes. This understanding is crucial in fields ranging from pharmaceuticals, where precise control over chemical reactions is necessary, to nanotechnology, where the manipulation of atomic properties can lead to groundbreaking materials and devices. The theoretical understanding of electron arrangement and ionization energy has practical applications that permeate everyday life. From the development of new pharmaceuticals to the creation of advanced materials, the principles derived from the shell model and atomic theory guide crucial innovations. In medicine, understanding how electrons interact within and between molecules allows chemists to design drugs that can effectively target specific biological pathways. For instance, cancer treatments often involve drugs designed to interact with the electron configurations of specific molecules within cancer cells, disrupting their function and inhibiting cell growth. In materials science, engineers use knowledge of ionization energies and electron configurations to create alloys and polymers with specific properties. These materials might be exceptionally strong, highly conductive, or resistant to corrosion, depending on the intended application. Such materials are critical in industries ranging from aerospace to electronics, illustrating the broad impact of atomic theory. The exploration of atomic structure and the behavior of electrons has not only enhanced our understanding of the chemical world, but also propelled technological advancements. One of the most significant areas of impact is in the field of electronics, where the manipulation of electron flow in materials forms the basis of virtually all modern devices. Semiconductors, the heart of electronic devices, operate based on the principles of electron movement and band theory, a concept directly related to electron configuration and energies. Engineers design semiconductors with precise doping to manipulate electron availability, enhancing device performance and efficiency. Furthermore, the development of new energy sources, including more efficient solar panels and batteries, relies heavily on insights gained from atomic theory. By understanding how electrons transfer between atoms and molecules, scientists can create better energy capture and storage systems, crucial for advancing renewable energy technologies. As we continue to delve deeper into the atom's mysteries, the future of atomic research looks promising and is likely to yield even more profound insights and applications. The ongoing development of quantum computing, for instance, relies on principles of quantum mechanics that govern electron behavior at the smallest scales. Advanced imaging and spectroscopy techniques are allowing scientists to observe and manipulate atoms and electrons with unprecedented precision. This not only enhances our understanding of the atomic world, but also opens up new possibilities in materials, science, medicine, and technology. The potential for discovering new materials with novel properties, such as superconductivity at room temperature or materials with ultra-high tensile strength, continues to drive research in atomic physics. Such breakthroughs could redefine industries and lead to technologies that we can scarcely imagine today. In conclusion, the exploration of the shell model and the broader field of atomic structure has far-reaching implications across science and technology. From enhancing our understanding of the universe at a fundamental level to driving innovations in medicine, materials science, and beyond, the insights gained from studying electrons and their arrangements continue to shape our world. The principles of ionization energy and electron configuration not only deepen our understanding of the chemical elements, but also provide the foundation for advancements in various technological fields. As we uncover more about the atomic world, we pave the way for future discoveries that will continue to expand the boundaries of science and technology. The journey into the atom is far from over, and its continued exploration promises to unlock even more secrets that could revolutionize our approach to solving some of the world's most pressing challenges. The profound impact of this journey on human knowledge and capability is a testament to the power of scientific inquiry and the endless curiosity that drives it.